So I should just start out by saying happy birthday to my mom, if she's watching. I don't know if she is. She wanted to come today, and I said, no, you can't. I just don't think I could deal with having you in the audience. So anyway, who knows? Maybe she's watching or maybe she's not. I did happen to send her the thing to the live stream, but anyway, I'll see her later tonight. Right. So I just wanted to start by, I lived in New Zealand for a really long time. One thing that I really miss about living there is that there's always a Maori welcome for everything. And so I wanted to start my talk by talking about the indigenous people in this area. And there's two tribes, the Piscataway Indians, who I think have been in the area for 30,000 years, and the Pamunkey Indians. So I just wanted to start and mention them. And then I wanted to thank Ben and Kelly for all their hard work. And then I wanted to say, let's see, how do you change it by, where do you change this? Is it over here?
Sorry, so here,
I don't actually know.
green going forward, red going back.
Okay, this is how we change the slide. Sorry, I didn't know. Anyway, and then I wanted to say that that I based this talk on a blog post by Thomas Lumley, and he based it on a blog post by Robin Spear, who I think works in Python, and it's also a chapter in deep learning in Azure. So right now let's see. Oh, there we go. So algorithms are kind of everywhere, right? And some of them are good, some of them are bad. One that I want to talk about is baseball algorithms. So there's lots of data for baseball. You know what? I don't see my time. Is there a place? I'm okay? Yeah. But I just would like to know.
Okay.
Sorry, I'm like, anyway. Okay, here we go. So anyway, there's baseball, and baseball uses a whole bunch of data. And so for example, the first time that someone really used and observed what was happening and altered baseball using data I think it was in the 1940s or something like that. And there was this guy that always hit home runs and always, and it was really hard to beat. And then one of the coaches recognized this, and he's like, well, why don't we just switch around these players in this corner where he always hits? And then they ended up getting him, and catching all of his balls and getting him out a lot more. Thank you, Ben. Sorry for being so difficult. So anyway, right. So that is baseball, and I mean, I don't know how many of you watch a lot of baseball and know a lot about baseball statistics. It's not something that I'm very familiar with, but everyone knows that what's going on. Everyone knows kind of everyone else's statistics, and everyone kind of, it's kind of like very open, right? And that's an example of a really good algorithm. And in addition to that, say for example that you're looking at certain players and you're like, I don't want to take this player, and then you find out that he went to some other team and he did really, really well, or they did really, really well, and then you look at your algorithm and go, well, what's wrong with it? How can I tweak it to make sure that I don't miss that person next time? So, or someone like that next time. So that's an example of a good algorithm. It's open, and and everyone, people know about it, right? And it's not secret. So another example for that is, I'll just talk about the second one, which is Amazon. Does anyone know, has anyone heard about how Amazon, if you submitted your CV to Amazon and you were a woman, that you automatically rejected because the data set was trained on all males? and so that's an example of an algorithm that didn't work very well, right? And that kind of came out in the public and people recognized that, but there's something wrong with that process of building an algorithm like that, right? So us, as data scientists, we have to be really careful about these kind of things and think about them. Another one that was really poor was Michelle Rhee. Does anyone know Michelle Rhee? We're in DC. Yeah, so some of you know about Michelle Rhee. So it was value-added teachers. The DC school system was not doing well, and so they decided that they were going to fire all the bad teachers, And so they wrote this algorithm, and what they decided is that students' test scores should increase. They should go up kind of in this some kind of fashion, I don't know. And then what ended up happening is, you know, it's a very high stakes test, and some teachers weren't very honest. You know, they ended up scrubbing out some of the answers and putting in the right answers, and there was and a lot of the teachers were, you know, a little bit worried about, you know, math and stats. So they kind of have this, you know, there's kind of this math phobia in the world, and it kind of, we have to get us, the people who are here. I don't think you have it. So we need to be the ones that are thinking about these algorithms and asking these questions, right? So, and what ended up happening in that case was that there was a woman who saw this group of students come in, and she said, "I don't believe these test scores." And sure enough, you know, the end of the year, the students didn't do as well, as, you know, they didn't increase as much as they should have, and she was fired, and she quickly went to another school. But the problem with that algorithm is it's secret, and also the teacher that went to the other school, they didn't keep track of her later to figure out if how her performance might have changed to really alter and adjust the algorithm so that it didn't have, you know, and this is, you know, of course, like false positives and true negatives that I'm talking about. So, you know, a lot of algorithms and statistics, we deal with this kind of, you know, type 1 error rate and the power and stuff like that. And so it's managing that when we have these big, huge algorithms can be a lot of people that are misplaced or misclassified. Okay, so these algorithms are, you know, important. You know, the poor algorithms are important, they're secret, and they're harmful. And this is just my slides, and there's a few more things there. I could go on talking forever, and I'd like to spend some time talking about the solution. So let's see, green, here we go. So this is, I don't know, how many of you know who Ross Ihaka is? A few of you do. He wrote R. so R is called R because Ross wrote it, and he taught me R. And I told you I lived in New Zealand, and one thing you may not know about Ross is Ihaka is a Maori word. It means Isaac. So Ross is himself Maori, and I think that's part of the reason that there is a big community in R. I think is because I think he was part of the Maori culture is to be kind of a little bit more open and inclusive and stuff like that. But anyway, I was really struggling with something on my computer, and I was so frustrated. I was like going crazy. And I went to Ross's office, and he just looked at me and he said, "What do you think he said?" Yeah, he said computers are stupid. So, and that's the problem. Computers are stupid, you know? And the best people that we know that come up with great things know this, right? So computers are stupid. And then this is Joan Woolcombe, who she wrote this she was a Times of London columnist, and she wrote an article in 1970 that said, "Computers need people." That was the title of the article. And kind of prior to this, there was a big shift about this time where people recognized that, prior to that time, they kind of thought that computers were a little bit like typewriters. That you just needed to do this. And so there was kind of this big shift about this time to recognize that the people that worked with computers were actually adding a lot. Okay? So anyway, there we go. So our current workflow is like this. But, I think this is really great for undergraduate courses, right? You import, you tidy, I don't know if anyone hasn't seen this, but this is something that Hadley, Wickham, and Garrett came up with. But if you look here, we have this model, and sometimes the model sometimes models aren't accurate, and so we need to think about a way to deal with these models that might be a little better. And I like to think about it, so we have a process called cleaning data, and I like to think about it as having a clean model, right? A model that is clean, that has kind of positive reinforcement loops. Right. So here's another possible workflow that we can have, and that is we have the model, and then we try it on a really different data set if we find that we need to, or maybe we clean the model back and forth. We just try a few different things. I really don't know what kind of workflow, better fits, like this baseball algorithm that's a really positive algorithm. But I think, anyway, I just thought, for me, I'm a visual person. I like to think about this. So let's all take a few deep breaths, because the next part of the talk is going to be a little bit difficult. This is where I get into my trigger warning, where I almost had PTSD from my experience this week. So let's all take a few deep breaths and breathe. I'm going to talk about a really sore spot right now, and that is dealing with Python. So this is Python. And I was really trying to get I'm really sorry, the HDMI cable at this venue is not working, so I couldn't show you my experience with Python today, but, or on the computer. I just had to put it in, I just had to edit my slides while the last speakers were talking, because I couldn't show you this. But this is my time with Python, and everything, it was, I'm still recovering. And I wanted our last speaker, Martin. It's really interesting that this is the community section, because Martin and I worked on it like tirelessly this past week. We spent a lot of time working on it, and actually the problem that I had with Python was trying to get it was installing and importing the modules, which is their packages, into the right Python version that Reticulate was talking to. So it was very, and this is the kind of things you do as a data scientist that you never really get trained for, and you just have to kind of try to figure it out yourself. And of course, in the end, what did I find out? That I just had to turn my computer on and off, and somehow it just magically worked. So, and I'm sorry that I don't get to talk to you about it a little bit more and show you it, but I wanted to show you the sentiment analysis tool that Thomas Lumley was my PhD supervisor, that he built in his blog, and I wanted to talk to you about it because it's so simple. It's probably like 30 lines of coding or something, and I wanted to show you how simple it is to build something that, although it predicts well for the training set, might not do well for other data sets. So here we go. So this is the sentiment of these words, positive or negative. And, so this is the testing set, and I just randomly chose some and put in their predictions, and it looks like it's pretty good, right? So if I were looking at this model, I would say I think this looks pretty accurate. But then we need to, the point of my talk is that we need to think a little bit more, right? Because computers are stupid. So computers are stupid, and we need to think a little bit more. And here we go. So here's perhaps a problem with this model. So it's okay, it's pretty much okay with going for Italian food. It's a little bit less like Chinese food, but it doesn't really like Mexican food, right? And why is that? Does anyone have any guesses? Well, that's a 5-letter word that could have something to do with it. You're right. And so the point is that the language that we use, and this was trained off of the data set I downloaded and worked with this for was from Stanford. The same thing happens on the Google data set, and Robin Spear works for the company ConceptNet. They're at MIT. Actually, I don't know if it's a company or what, but it's called ConceptNet, and they have another data set that they're using called number batch, and the idea is to reduce these kind of biases, right? And I was going to kind of try to show you that in the reticulate package, but there were other plans, so we don't get to see that today. But here's another issue. So I just picked some random names, obviously Kelly and Ben, and they kind of like Kelly and Ben, but they don't like Shaniqua, And I would like to live in a world, and I think a lot of people would like to live in a world where, what a computer and algorithm thinks about us is more who we are, right? And not what our name is. Just an idea. Anyway, so the point is that if you're building these tools, it's important to do these kinds of tests. And this is the kind of thing that I was talking about back here. This one. So I'm putting in these new variables here, and I'm kind of cleaning it to check it, right? If I trained it on the new data set from number batch, that would be more like this one. Oh, this doesn't work, so I'm going to train it on a different model. Okay, so how do we learn what kind of things to put into these models to test to make sure that they're okay? And I think we have to really think a little bit outside the box. And it takes practice, and it takes experience, and it takes creative thinking. So here we go. So I'm sorry, it's a little small. I don't think you can read it. This is something that's popped up on Twitter today, and I'll read it to you. And this is a person that works in AI, and its recognition of it recognized the picture. So the bot was trying to caption the picture, and it says, a couple of giraffes are standing in a pin. It says P-I-N, it doesn't say pen. Anyway, and then the person asks the bot, anything else? And the bot says no. And the person says, no people with lightsabers? And it says no. And then the person says, how many giraffes? And the bot says 2. And how many giraffes? It asks again. 1. How about giraffes? How many of these? 1. And then it says any giraffes, and it's 0. So although it looks like it's doing the right thing, it really is. Computers are stupid. I don't have anything more to say. Right? So here we go. Let's move on. So we can talk about cleaning or auditing an algorithm so you can get more data, retrain it. Don't keep it secret, right? People can know, like for another good example of a good algorithm is your FICO score, which is your credit rating. It's, you can go online, you can find your FICO score. You're supposed to check your FICO score, every year and figure out if there's any errors in it. It's very clear how to improve it or how not to improve it. And stuff like that. So it's important. It's important, that people have choices and feel like they have power. And us that are more numerate need to, or we could. I feel that I need to make sure that these kinds of things aren't happening. The other thing that Kathy O'Neill wrote. She's the author of Weapons of Math Destruction. I don't know if you're familiar with her, but I heard an interview. Matt actually, our first speaker, posted something about her on Twitter about an interview, and I've quickly took notes. But she talked about an ethical matrix. So when you develop an algorithm, have an ethical matrix and include your stakeholders. So who, for example, if maybe perhaps we would have come up with a very different algorithm and perhaps a more effective algorithm if we had asked teachers how they should be, how we could figure out how much value they add to a student. I don't know. And of course, example of an ethical matrix may just be, I am the stakeholder and my main concern is making money. That's all I want to do. And that is one, that's how we ended up in the economic, the financial crisis in 2008, is that everyone wanted to make money. And so, yeah, I think that's all I have to say. So thank you for letting me talk.